Solving trig equations. You probably realize that we have indeed been solving various different sorts of trig equations. So why is there now a special section about solving trig equations and what's new about it? So the trig equations we've solved so far have generally been for a range of angles falling within a specific range, such as 0 to 360 degrees, and not really taking periodicity into account. But what's new now is we'll take periodicity into account to determine the general solution of a trig equation. And in line with that goal, it's worth just revising what the periods are for the different trig functions, starting with sine. So that's a graph of the sine function. Don't worry so much about this line, I just pasted the exact same graph from earlier on. But the main point is the period of sine theta is 360 degrees, because every 360 degrees you have this whole shape repeat itself. And the cosine function is very similar and has the exact same shape, except it's offset by 90 degrees. But since it has the exact same overall shape, every 360 degrees the graph repeats itself. Therefore, the period of cos theta is also 360 degrees. Then last is tan theta. And the period of tan theta is 180 degrees, where every 180 degrees, this whole shape repeats itself again, where it starts with a vertical asymptote at negative infinity, then continually increases and increases, finally ending with another vertical asymptote at positive infinity this time. Then it repeats itself, starting with a vertical asymptote at negative infinity, and so on and so forth. And this happens every 180 degrees. And let's see how we'll take the period into account with a few examples. This question says that sine x is equal to 0,5. Then what is the value of x? So this is a similar example as the one covered in the fundamental section, but the only difference is this time a range of theta values isn't specified, and it just asks what is the general value of x. So you solve it using a similar bunch of steps as before, where first you determine the reference angle by taking sine to the other side and making it sine inverse of 0,5, which gives the reference angle as 30 degrees. Then the next step was you need to note the sign of the function value. This time it's sine x is equal to 0,5, so the function has a positive value. Then the third step was check which quadrants the function has the sign from the second step using ASTC. So sine is positive in the first and second quadrants. Then the fourth step was determine the other angles by applying the quadrant rules. So first we know it will be in the first quadrant, for which it will just be equal to 30 degrees. Then here's a new step where to finalize this as a one solution, you need to add in multiples of the relevant period. Since we're dealing with sine over here, the period of the sine function is 360 degrees. So to finalize this as a general solution, you add in multiples of 360 degrees, like this, where k is usually the letter used to represent a multiple of the period, and k needs to be an integer, meaning a whole number. It doesn't matter whether it's positive or negative. Either is fine, but k just represents an integer value. So meaning 30 plus any integer multiple of 360 degrees will satisfy this equation. So you can start with k value of 0. So that will just give 30 degrees, which we already verified as a solution. Then if you try a value of 1, this would give you x as 390 degrees. And if you check sine of 390 in your calculator, you'll also get 0,5 as the answer. So that would also count as a solution. You can try it again with negative values, and so on and so forth. So that's the first quadrant value. Then the other possible general solution is in the second quadrant. And in the second quadrant, the rule is 180 minus reference angle theta. So this would be 180 minus 30, meaning 150 degrees, which is the second possible solution. Then to finalize it as a general solution, you again repeat this extra step of adding multiples of the period for the function. We can think of this extra step as a fifth step added onto the previous 4 from earlier on. Then as a final step, you can verify all your solutions using a calculator. So we previously checked a few cases for this 30-degree solution, and then for the 150 degrees we can try a k value of say 7, which when multiplied by 360 degrees and added to 150 degrees gives a value of 2670 degrees. Crazy number, right? But it should also work for the solution, which you can verify by saying sine of 2670, which you'll see also gives a value of 0.5. So our second solution also checks off. Then here's another example. Determine the general solution of tan b equals to minus square root of 3. So again, first determine the reference angle, which you can do by taking tan to the other side and making a tan inverse of root 3. Remember, as earlier stated, you remove the negative sign when you do the inverse function, but just note somewhere on the side that the function is equal to a negative value. And when you calculate tan inverse of root 3, you get an angle of 60 degrees. Then you carry out the second and third step. The second and third step can kind of be coupled into one, where you note that the sign of the function is negative, and then realize that tan is negative in the second and fourth quadrant. Then you go for the next step, which is applying the quadrant rules for the relevant quadrants. Where for the second quadrant, the rule is 180 minus reference angle, so 180 minus 60, which is 120 degrees. And then I just automatically coupled it with the extra step of adding in multiples of the relevant period, where since we're dealing with tan in this case, the period is 180 degrees. Then for the fourth quadrant, it would be 360 minus 60 degrees, giving a value of 300 degrees plus k times 180. Then here's something which they could try to catch you out on in exams, and you can maybe lose a mark or two. Try and assess the different solutions and how much they relate to each other. Because if you look at the first solution here, when you try a k value of 1, this would be 120 plus 180, and that'll just give a value of 300. So you don't have to have the two written out. You can just combine the two and summarize them as b equals to 120 degrees plus k times 180. So that's your solution, and just for your own assurance, you can check a few possibilities using a calculator. So I've already tried one positive value of 1, so this time I'll try a negative value. So say k is equal to negative 1, which gives b as negative 60 degrees. And when you calculate tan of negative 60 degrees in your calculator, you get negative root 3, as was required. Then here's another example. Determine the general solution of cos w is equal to sine 2w. This is more the sort of question you could get in an exam, and it has a few new important aspects, so pay close attention to this example, because I'll raise various important points that will help you going forward. So the first step is, how do you solve for this? You can't say cos inverse sine 2w, or you can't take sine the other side and say sine inverse cos w. So how do you go about solving this? So the idea is, make them both into the same function. So you can do this by saying sine 2w is equal to sine 90 minus w. And then now at this stage, you can equate 2w to 90 minus w. But an important new aspect to keep in mind is that at this stage, essentially what's happening is you're sine inversing both sides. And when you do this, you should already start thinking about what quadrants the solution will fall inside. So for 2w equals to 90 minus w, both are positive values. So you can tell that it's a sine function and it has a positive sign, meaning it would fall in the first and second quadrant. So you should just note that somewhere on the side. And then another thing is, this is your basic solution. It's a little tough to explain, but you just think of this whole 90 minus w term as just being your reference angle theta. And what you do is, at this stage already, you would add the multiple of the relevant period, which would be 360 degrees for sine. So we know the solution will be in the first and second quadrant. So in your first quadrant, you would have your 90 minus w, or theta as it were, as it is, and plus k times 360. Then you go about solving for w by rearranging it. So you take this w to that side, giving you 3w equals to 90 plus k times 360. Then you just divide both sides by 3. So you divide this 90 as well as the period and its multiple, giving w as 30 plus k times 120 degrees. And that's your first solution corresponding to the first quadrant. Then for the second quadrant, remember I said that you think of this as being theta. So for the second quadrant, you have 180 minus theta. So in this case, that would appear as 2w equals to 180 minus 90 minus w, plus the multiple and the period. So that's your second basic solution. And now, as you did for the first one, you can make w the subject and you can do the calculation to get the solution. So in this case, it will become 2w equals to 180 minus 90, which is 90, and minus of minus w, so it would be 90 plus w. Then you take this w to that side, leaving just a w on the left, giving the solution finally as w equals to 90 degrees plus k times 360 degrees, which is the second solution corresponding to the second quadrant. And this solution is unique from this one. You can't summarize them both into a single answer. So this whole process is probably still a bit confusing, so we can look at another example. Determine the general solution of sine alpha times tan alpha is equal to 1. So clearly this needs to be rewritten a bit to turn it into a form that we can solve. So the most obvious change you can make first is change tan alpha to sine alpha over cos alpha, which would give sine squared alpha over cos alpha. Then we can try to represent both the numerator and the denominator. So I'll just change this sine squared alpha to 1 minus cos squared alpha, giving 1 minus cos squared alpha over cos alpha. And this would all be equal to 1. Then you can multiply this across, giving 1 minus cos squared alpha is equal to cos alpha. And if you bring everything to one side, you get cos squared alpha plus cos alpha minus 1 is equal to 0. So that's interesting. If you think of cos alpha as something like x, this basically represents a quadratic equation, which would be of the form x squared plus x minus 1 is equal to 0. And we can solve this using the quadratic formula, which is minus b plus or minus square root of b squared minus 4ac over 2a. And the next step, if you remember from the polynomials video, is write out the values for a, b, and c, which in this case would be 1, 1, and negative 1. Then simply sub them into the equation, which when you simplify comes to minus 1 plus or minus square root of 5 over 2, which gives the answers to the quadratic equation as cos alpha is equal to 0,618 or minus 1,618. And from our knowledge of the cos function, we know that there's no angle for which cos alpha will equal to a value less than negative 1, such as negative 1,618. Therefore, this cannot be considered as a solution. So it means the answer is cos alpha equals to 0,618. And we can finally now solve for alpha and go through the whole process as before. So first, take cos to the other side and say cos inverse of 0,618, which gives a value of 51,8, which is essentially the reference angle. Then we can go to the next step, which is realize that This is a positive function, and cost would be positive in the first and fourth quadrants. So for the first quadrant, the solution would be 51,8 plus k times 360 degrees. And for the fourth quadrant, it would be 360 minus 51,8, or in other words, the reference angle, plus k times 360 degrees. Finally, giving the second general solution as 308,2 plus k times 360 degrees. And I won't go through it myself, but you can personally verify it using different k values on your calculator. Then for the final section of trigonometry, we'll look at geometric applications of trig functions.